Good morning, everybody, and welcome to the IBM Qiskit Quantum Seminar Series dedicated to you, the research and academic quantum communities. Now, we're going to keep it right to the punchline today, and I'll be thrilled to roll out this week's episode with Eliot Kapit on a very interesting question. Now, we usually like to give people about a minute or two to tune into the live stream. So, you know my favorite question, which is, where are you guys tuning in from today? I'm back in my usual spot in New York City. You can reply to that on the comment chat box located here on YouTube, somewhere above, below, left or right on your screens. Now, that is the same place where you can also ask questions live of Eliot and myself during the presentation, and we can keep it lively and a discussion. That allows us to really only get interactive at Friday at noon Eastern Time. You can always go back and rewatch these and check out what the videos of previous episodes are. I think this is episode number 165. 165. I have to say that twice to remind myself how many episodes that is. And folks, as always, click like and subscribe to know what's coming up. So with that, let's just dive right into it today. We'll keep the intro short. It's my pleasure and privilege to welcome to the stage here Eliot Kapit. Hello, Eliot. How are you today?
Hi. Thanks for having me.
And Eliot, do tell us, where are you tuning in from yourself?
Golden, Colorado, just west of Denver, the home of Colorado School of Mines and the Coors Brewery.
Golden, Colorado. That sounds like a great place. And I see here in the chat we have people from Troy, New York, from Poland, New York City, Istanbul, Costa Rica, India, many places. So thank you, everybody, for making all the different time zones. Durham, North. Hello, Sam Ferry. Taiwan, Sao Paulo. So really, you have quite the audience today for your very nice talk. Before we kick it off, allow me to introduce you briefly. Eliot Kapit is an associate professor of physics at the Colorado School of Mines and director of its interdisciplinary quantum engineering programs. Eliot received his PhD in physics from Cornell University, just up the street here, and metaphorically speaking, and did postdoctoral
4
work
hours by
at
bus.
4 hours by bus. Yes, yeah. I think Cornell. My friends at Cornell always tell me it's less, but usually my experience is it's more.
Yeah.
And did a postdoctoral work at Oxford and the City University of New York before starting a faculty position at Tulane University. From Tulane, Eliot moved to Mines, where he has worked ever since. So with that, the stage is yours.
All right. Let me share my slides, move around. All right. So thank you, everyone who's tuning in from all over the place. And thank you very much to Zlatko and IBM Quantum for giving me the opportunity to talk to you about all this. So what I'm going to be talking to you all about today is what I think is a really important and underappreciated question to which I do not have a complete answer, which is what ensures approximation hardness for quantum algorithms. And I'm going to be presenting work from a paper. The archive link is right there. It's by myself, 5 very excellent Mines students, many of from our quantum engineering program and physics program, many of whom have already graduated and gone off into the world to other things, and with Lincoln Carr from Mines and my longtime colleague and collaborator Vadim Oganyesin from City University of New York. So as an outline, I'm going to first introduce what I mean by exact and approximate optimization hardness in these hard classical problems to which we're applying quantum computers. Then I'm going to introduce the max3 exersat problem that we studied in this work, which I think is a uniquely good problem to consider for this purpose. I'm going to discuss the results we have about why we think adiabatic quantum computing and very likely QAOA are weak approximators for these problems, present quite a bit of numerical results backing that up, and then introduce our new set of spectrally filtered quantum optimization methods, which were designed to solve the problems we identified in AQC and show dramatic performance improvements, and then sort of offer some conclusions and discussion. Okay, so just to ground the discussion, the problems we're interested in here are very hard problems in the complexity class NP. And NP is the set of computer science problems where checking an answer is easy in that we can do it in polynomial time and the size of the problem, but finding the answer is super polynomially hard in the worst case, generally because the search space is so vast. And a problem is said to be NP hard when all problems in NP can efficiently be mapped with, efficiently means polynomial overhead in the language of computer science, to instances in it. And this need not itself be an NP. This could be something that's in an even harder class. And a problem is NP complete if it's a problem that is both NP hard and shown to be in NP, like 3-sat or traveling salesman. And we focus on these problems because we don't know how powerful quantum computers really are for these. It's likely that NP is not contained in BQP, which is the set of quantum algorithms that run in polynomial time and resources. That's not known for sure, though. But more broadly, quantum computers, are very much something that's still in its field that it's in its infancy in terms of the hardware, and we're just now starting to be able to perform useful tasks beyond what classical computers are capable of. And problems and in general, we only want to use a quantum computer if the underlying classical problem is too hard, because otherwise we would just solve it with traditional supercomputers. And the subset of problems in NP I'm interested in are what are called constraint satisfaction problems, which are defined as a problem of n variables and n sub c constraints, where each constraint is some very simple function that returns satisfied or not satisfied that involves just a few of the variables, typically 2 or 3 at a time. And an absurdly large number of problems can be written as CSPs. And there are exceptions, of course, but generically, if someone just hands you a CSP and says, write an algorithm to solve it, it's NP hard. And the proofs of hardness, I should say, are generally by implication. You can often argue, well, if I can efficiently solve class X, then I can map every instance in Y to class X, and I can map every instance in 3-sat to class Y, and we know 3-sat is NP complete, so therefore our original problem X must be NP complete or NP hard. But that doesn't explain actually why these problems are hard, right? It's, assuming P is not equal to NP, which nearly everyone, including myself, believes, but we've never actually proven. These are worst case statements. And in practice, many of these problems are easy. And to illustrate just how powerful the ability to solve arbitrary CSPs would be, I found this image of the 80-round SHA-1 algorithm, which is very close to SHA-256, the algorithm that Bitcoin runs over and over, written as a CSP here. And so if you could efficiently solve that, you've broken all of cryptocurrency and things like that. Again, I don't expect that we can, but being able to solve CSPs efficiently would be, or even better than classical computers, would be potentially transformative for all kinds of applications. But I think what's sort of less well known about these CSPs is that they're often also hard to approximate as well. And this comes from a theorem called the PCP theorem, where PCP stands for probabilistically checkable proof in classical computer science, which basically states that for every NP hard CSP class, finding configurations with energy or solution quality or whatever term you want to use below some constant fraction A of the global optimum, where A depends on the problem class, is NP hard. And you prove this by a technique called gap amplification, where you define polynomially larger versions of a problem. And if you can find approximate solutions to those larger versions, you can reconstruct the answer to the original problem. I should say that this is not usually a practical way to solve hard CSPs, and I've spoken to quite a few people working on the bleeding edge of optimization, and no one was aware of a single solver that used gap amplification. So this isn't a practical way to solve these things in practice, but it's important because it puts formal constraints on how powerful computers can be for solving these problems. And it's good to ask, though, why is approximate optimization hard? And the answer comes from a phenomenon that was termed entropic barriers in this paper by Matteo Belletti and collaborators in Physical Review Research in 2021, which basically states that if we think of the space of all possible configurations as a landscape, it's rough with lots of local minima, and there's a large energy cost to escape. And finding any one minimum is easy. You basically just pick a random configuration and do steepest descent, updating the, flipping variables until you can't lower the energy anymore and halt. But if you find one minimum, that doesn't give you any information about deeper minima elsewhere. And so the analogy I like to use, I come here from Colorado School of Mines, which is right at the foothills of the Rocky Mountains, would be that if I blindfolded you and said, okay, I'm going to drop you somewhere in the Rockies and I want you to walk to the top of the highest peak, right? You can very easily find the top of a hill and may very easily find the top of one of the smaller mountains if you happen to be near it. But finding the very highest 14er is another matter. And unless you happen to have a lucky guess where my helicopter dropped you right next to the peak of the tallest 14er, which embarrassingly I don't remember which one that is at the moment, you're not going to find it, and it's going to take probably millions of years of wandering. Basically, in the computer science terms, it's that local minima provide no guidance to deeper, higher quality solutions. And it's often better to just restart. You just keep doing random guesses and relaxing until you happen to get a good guess that was close to the deepest minimum. And so therefore, finding approximate solutions are, in the worst case, requiring a lucky guess that's sitting in an exponentially small fraction of the search space. And exponential runtimes result. And for any algorithm that's based on local updates, including more sophisticated versions like simulated annealing and parallel tempering, this is the same classical mechanism as exact solution hardness. So the mechanism that makes it hard to find the exact ground state is the same mechanism that makes approximation hard in the worst case, at least intuitively. And what I'm going to show you, though, is that that's not true for quantum algorithms, and the mechanism that ensures approximation hardness is going to be something weirder and more obscure. The problem that we're going to talk about today is something called max 3 exersat. And 3 exersat is defined as a sum of 3 body constraints, where each constraint is a product of 3 Pauli z's, and so it returns plus minus 1 on some arbitrary hypergraph. And each of these constraints has a coefficient plus minus 1, and the goal is to get the largest number of constraints returning plus 1, finding whatever bit string does that. And a random string satisfies half the constraints and has energy 0 in this language. Checking if a given instance is fully satisfiable turns out to be efficient. You can use an algorithm called Gaussian elimination and exploit the linearity of the problem. But as soon as it's a little bit unsatisfiable, Gaussian elimination returns nonsensical results. And now finding whatever is the closest to fully satisfiable, so the closest configuration to all constraints returning plus 1, is NP hard. And there's a theorem by Johann Hastad that says that if the optimal configuration satisfies a fraction 1 minus epsilon of all the constraints, then finding any constraint that any configuration satisfying 1/2 plus epsilon, where again 1/2 is what you get from random guessing, is NP hard. And so therefore the hardest instances to approximate are those that are almost satisfiable, where epsilon is not 0 but very close to it. And in that limit, the threshold A can become very close to 0, e.g. the random guessing limit. And the nice thing about max 3 exersat is that it's one of the hardest low-order CSPs in practice. And when you do simulations of both classical and quantum algorithms, you can see the exponential scaling at small n, like around n equals 10 and higher, which is in the range where typically the range 10 to 30 is the range that you can simulate quantum algorithms classically. And so if you're trying to develop an algorithm and benchmark it numerically, so for future use on fault-tolerant quantum computers, so you don't have to worry about error, you want something where you can do some simulations either as a sanity check, or if you can't make theoretical predictions of how your algorithm is going to perform, try to estimate scaling and things like that. And you want to be looking at a problem where it's exponentially scaling in that regime. There are a lot of problems in NP where you don't necessarily see that. So like MaxCut is a famous NP hard one that's studied all the time. And in practice, you generally don't see the exponential scaling until hundreds or thousands of variables, which makes benchmarking, if I'm trying to write down a quantum algorithm to solve it fast, or claim that it should improve the performance at least, I want to be able to test that in the range where it's actually hard. And max 3 exersat that range lines up with where I can simulate things on powerful workstations. Our goal is to find what we would consider a typical case exponential speedup for approximate
Elliot, quick
optimization.
question.
Yeah.
If you go back to the previous slide, can you walk us through the graph here on the right? Is this saying?
Yeah. So this is I'm going to return to what this is. So this is basically the success probability per shot of this randomized classical algorithm that I'm going to talk about in a little bit, but it's for different problem parameters. And so I'm going to go over everything on that graph is. It's basically just showing, yes, it's exponential at fairly small n.
And it seems like there's some parameter which makes the black curve way more hard or difficult.
Yeah, and so it's constraint density, and I'm going to get to that in a few slides.
Okay, thanks.
Great. And so our goal is to find an exponential speedup for a typical case, so random hypergraphs in the approximation hard regime, and definitely not claiming this would apply to all instances. But we already have one problem, which is that random instances are empirically easy to approximate, if not to solve exactly. And the reason for this is if my problem graph is sparse, I can always get an approximate solution by picking an even sparser subset, solving that, because if these CSPs are sufficiently sparse, they become very easy. And then that solves half the remaining constraints. So I can always get an approximate solution to a fairly sparse problem. If it's a dense random problem with random signs, then statistically with overwhelming likelihood, although not all instances, the ground state satisfies NC, half the constraints plus order square root NCN. And there are classical algorithms that can return similar scaling above random states with a smaller prefactor. So just drawing a random higher density instance is not going to give me something that's approximation hard. To make an approximation hard problem, what we're going to do is we're going to choose a small unsatisfied fraction and plant a solution. So we use epsilon equals 0.1 throughout the paper and everything in this talk, but any small epsilon will work. And what we do is we choose a random hypergraph with NC much greater than n unique constraints. We choose some random bit string to be our planted partial solution, and then just pick the signs of all the constraints such that G satisfies a fraction 1 minus epsilon of them and is unsatisfied by the remaining epsilon NC. And this defines what we call a planted partial solution problem, and this was inspired by other previous constructions in the literature, and I forgot to put the citations on the talk, but they're in our paper. And the other nice thing about 3-exersat and max 3-exersat is the best known algorithm for this problem is very simple. It's a quasi-greedy algorithm from Belletti et al., which is essentially a tuned version of steepest descent. And steepest, there are hundreds of optimization algorithms for CSPs. Why pick the simplest one? Why not something more sophisticated like simulated annealing and parallel tempering? And the answer is that when in the empirical landscape of these random hypergraph problems has lots and lots of deep local minima, you find one quickly. It is very unlikely to be the deepest one or the one that is much deeper in the case of the approximation hard problems. And there is essentially no correlation with it spatially unless you happen to be lucky at the outset. So it's cheaper to just restart rather than try to climb out with thermally penalized operations. And there was a large solver competition on 3-exersat a couple years ago, and a version of this algorithm won, where it shows the same scaling as the same scaling exponent within error bars of parallel tempering, which is a much more sophisticated version of simulated annealing, but with a much better prefactor. And we're going to use this algorithm to benchmark PPSPs. But before getting into the details of how these algorithms perform, what I really want to highlight, this is the Qiskit Seminar, this is ultimately a quantum talk, is that quantum algorithms approach CSPs completely differently. And in this talk, I'm going to look at algorithms that simulate Hamiltonian time evolution. And these algorithms fall into the very, very broad class of quantum annealing, adiabatic quantum computing, QAOA, where basically I have a driver Hamiltonian and a problem Hamiltonian. And I initialize the ground state of a trivial transverse field driver. So all spins are polarized along X, and the driver Hamiltonian is a uniform transverse field along X, My problem is defined in the z basis, and I slowly ramp the transverse field driver down and the problem Hamiltonian up, and I measure the system at the end. And there are, obviously hundreds of variations of this with a very large time step and sort of broken into choppy discretized segments. You get QAOA with a very small time step. You get adiabatic quantum computing. In an open quantum system, you get quantum annealing if there's a thermal bath, and so on. And then, of course, you can more complicated driver Hamiltonians, warm starting, etc. There's all kinds of things you can do. But what I want to emphasize is that this is a radically different way of solving problems from classical methods, because all of these classical local update algorithms start at high energy. You start in a random configuration, and you try to cool to the ground state by flipping spins one at a time or in small clusters at a time to try to get to as low energy as you can. So you're starting at infinite temperature and trying to get to zero temperature, or at least something cold in the case of approximation hardness. Quantum searches start in the ground state of a different Hamiltonian and approach the solution from below by a quasi-adiabatic interpolation between these two different Hamiltonians. But of course, there's a catch, and the catch is that you have to cross phase transitions to do so. You have to transition from your simple what's called the paramagnetic phase, where everything's just polarized along x, to this quantum spin glass state. And unfortunately, in many cases, in fact, generally most cases, the scaling of the paramagnet to spin glass transition decays exponentially in system size. And this means that you have to move exponentially slowly or run your algorithm an exponentially large number of times to successfully make this transition and find your spin glass ground state. But there's actually, and this exponential scaling of QAOA, AQC, and so on is pretty well known. If you've done any meaningful amount of studying of quantum optimization algorithms, you've heard about it. What's less known, and I think more insidious, is a phenomenon that's called transverse field chaos. And this term, I believe, comes from Itai Hen, although he never actually wrote it in a paper. But I like the term a lot. It comes from a similar phenomenon called temperature chaos in classical spin glasses. And the problem with transverse field chaos is the following. Let's say we can circumvent this issue, right? Let's say either the problem naturally doesn't have an exponentially scaling first transition, or we have some clever modification to the algorithm that makes it scale as a low-order polynomial, inverse polynomial instead, right? That doesn't guarantee an efficient solution. And the reason for this is that transverse field terms don't preserve spectral continuity, and the energetic corrections from them can push local minima of your spin glass problem below the true ground state. And that means your system is steered into those first, these low energy but not the true optimum configuration, and your system transitions into those first, and then the transitions to the true ground state occur late in evolution at much weaker fields and also have exponentially small gaps. And these gaps are, as I said, are exponentially small, and you can't predict them a priori. The problem of predicting if all of these things, if transverse field chaos will occur or not, is formally harder than solving the problem classically. But combined with small gaps, this likely ensures that no polynomial time method that looks anything like things in these class is going to guarantee success in finding the ground state. Because you can never rule out transverse field chaos. So even if you can somehow rule out that first transition being exponential, that's not enough. And this is believed generally to be the true limiting factor at large system size for algorithms of this type. However, for these planted partial solution problems where you have one minimum that's much deeper than all the others, you don't need to worry about transverse field chaos because there aren't other competing near ground states far away. And so you're limited by this single paramagnet to spin glass transition. And perhaps remarkably, we can actually predict this for random hypergraph problems. And there are two things that you need to predict the scaling of the transition. There's the cost per flip curve for x, random sequences that are x bit flips away from the ground state. and there's the transverse field strength at the phase transition, assuming we've properly normalized our problem so that random states are energy 0 and the ground state is minus n. Is energy minus n. And this normalization, I should say, becomes really important to the more sophisticated algorithm we're going to propose later. But fortunately, even though you don't know what the ground state energy is going to be a priori, there's only order nc values it can take, where nc is the number of constraints. So I can just keep guessing with a factor of nc overhead. And it turns out that what's really beautiful about these problems is this random cost per flip curve that I claim is so important to the transition is actually hypergraph independent and true for all problems. And it can be found from simple statistical arguments that the energy x flips away from the ground state is equal to the ground state energy times quantity 1 minus 2x over n to the power p, where p equals 3 is the order of constraints. And from this, we can use fourth order perturbation theory to predict where the crossing point is, and it occurs at around transverse field strength 1.3 if the problem is strength 1. And the minimum gap scales as the overlap of the paramagnetic uniform superposition with the dressed ground state. And we can actually calculate the dressed ground state as well using higher order perturbation theory, the expressions here, and this is gone through in much more detail in the paper. We then, just replacing these energies with their averages, we can then basically evaluate this function analytically for a whole range of n. This is a simple function to evaluate in Mathematica. You can evaluate for a range of n and then fit that to an exponential. And this is best fit by the function root n 2 to the minus 0.14 n. And if we have a diabatic sweep, which means our runtime is not scaling exponentially, but as some low order polynomial TF, we just use linear here, then the probability of finding the ground state at the end of an algorithm scales as the runtime times, and assuming the time step's not too small, not too large, so you didn't have Trotter error and no heating, etc., or noise. The probability of finding the ground state scales as this minimum gap squared over some energy range W that's order n, so exponentially small. And so having made that prediction, we want to benchmark these instances to show that we're actually looking at something hard, both classically and with quantum algorithms. And so first thing we're going to do is we're going to look at the traditional methods. So we're going to compare high depth trotterized adiabatic computing, or TAQC for short, and this quasi-greedy classical algorithm for planted unsatisfied fraction 0.1 random hypergraphs and constraint density of either 2, 4, 6, or 1.5 root n. So the total number of constraints is n times that. And the first thing we're going to look at is the quasi-greedy algorithm and just ask, okay, we run this, it's going to halt at a minimum. What's the probability that minimum is a ground state? And you can see that in all cases, this is decaying super polynomially. And what's really striking classically is that the problem is getting easier and easier the more extremal it gets. So the further we are into this planted solution range, so the higher the constraint density is for this fixed unsatisfied fraction, the easier the problem gets classically, although it's still scaling exponentially. And again, I only use this method because, as we'll see, it's really good for diagnosing approximation hardness in a few slides. But we only use this method here, but the scaling for the other, like parallel tempering and simulated annealing, is expected to be the same. Quantum algorithms, and this is basically, we interpret this as the basin of attraction. How wide is the sort of fan of states that will relax to the true ground state is getting wider and wider the more extremal the problem is. And so if we're cooling from high energy, we expect that if the basin of attraction is getting wider, the problem should be easier. Although again, easier means softer difficulty exponent, still scales exponentially. So it's not an easy problem in any context once n is sufficiently large. Quantum methods, though, approach the solution from below and aren't necessarily very sensitive to all this high energy stuff. And so if we look at trotterized adiabatic quantum computing, we see that the scaling is almost completely independent of constraint density. And so here, this is some pretty serious HPC work. These are linear total evolution time. So quadratic scaling number of gates. We simulated n between 8 and 28 for 4 constraint densities and 1,000 random instances per point. And so toward the end of this graph was really expensive. And so we obtained these using the QLAX package on the Fujitsu quantum simulator, where Fujitsu, the quantum simulator, is a classical supercomputer that's essentially a tiny piece of the Fugaku supercomputer in Japan. And Fujitsu last summer held this quantum simulator contest of basically who can find the most interesting thing to do on their supercomputer. And we ran these simulations as part of that contest. And notice the scaling collapse for finding the ground state with TAQC, which is predicted by theory. And that dashed curve is the average and is almost perfectly 2 to the minus 0.28 n, within error bars. So I see a question in the chat. What's the total evolution time here? I think it's n over 32. And I forget exactly what the time step is. All the details are in the paper, but it's scaling linearly. And there turns out that linear, runtime scaling at least linearly for these high depth algorithms is actually really important. I go into a lot of detail why that's the case in the paper, but it has to be at least linear. And so we picked linear. And also this scaling exponent for TAQC is much worse, right? The hardest classical problem we looked at, NC equals 2n, is already a quadratic speed up over the quantum method. So AQC is very poor for finding the ground state. But as I said, this talk's actually about approximation hardness. And approximation hardness is a different story. So we can similarly track the probability of that either algorithm halts at any state or returns any state below some fraction q times the ground state energy, where q is less than or equal to 1. And on the left is NC equals 2n, and plotting a whole range of fractions. And we can see that basically, if we look at 75 to 80% approximations, then our algorithm will return a state that is at least that approximation with constant probability. So it's very easy for this, this problem with NC equals 2n that's not all that extremal is also not hard to approximate. Anything below that starts scaling exponentially. For 4n, however, that achievability threshold QA has dropped to about 55%. And again, we're binning to bins of 5%. So this is not intended to be like a precision benchmark. And further, the scaling of almost everything below that has collapsed to the scaling of finding the ground state. So essentially for the approximation hard problems, with these relaxation methods, either you find the ground state or nothing close to it with nothing in between, because there's one minimum that's so much deeper than all the others. And if we look at 6n, we see the same. We see that the approximation threshold has degraded to 45% and everything decaying exponentially after that. And if we let NC over n scale as a root n, the approximation hardness threshold is decaying with system size. And so if we let NC over n grow sublinearly with n, QA actually goes to 0 and it becomes super polynomially hard to beat random guessing. So these instances are in the regime where they're actually approximation hard in practice. And we can do the same thing for adiabatic quantum computing. And I presume QAOA is going to give the same results, but we didn't want to do all the fiddly angle optimization. So we didn't look at that there. We see that for 2n, we can get a QA of about 75 to 80%. For 4n, it's 55%. And this is the same as the classical result. So again, QA is defined as what is the largest fraction where anything below it decays exponentially, but this doesn't. And for 6n, we get 45%, and for NC over n is scales as root n, we get something that appears to be decaying, at least within the sizes we can access in classical simulation. And the scaling exponents for these fits actually can in some cases be favorable and show modest improvements over what our greedy algorithm shows, but I don't really regard that as a meaningful quantum advantage because it's in this sort of narrow space of approximation hard planet solution problems. And the punchline here is that there is no significant quantum advantage for either exact or approximate optimization of these problems with trotterized adiabatic quantum computing, at least on its own. So just to review, TAQC and the classical greedy methods show the same asymptotic hardness thresholds. And we attribute this range where it becomes easy to be the energy above which local minima become dense, what we call the high energy clustering phase in the spin glass language. But it's important to ask, why is AQC weak, right? This talks about mechanisms, and we want to understand why is it weak. Well, the minimum gap to mix with the ground state doesn't decay that fast. Its square is 2 to the minus 0.28 n on average. And if we pick smaller q, there are way more than 2 to the 0.28 states to cross in that range. And it's similarly not transverse field chaos. Transverse field chaos involves crossings between states close in energy and can't ensure approximation hardness. So on its own. So at least as far as I'm aware, for any kind of problem I've ever heard of. So the two mechanisms that I identified as these are always in the worst case for algorithms that look like this, going to make it hard to find the ground state directly, don't ensure approximation hardness here, at least not obviously. So what does? Well, I can tell you what it is for TAQC, which is that, say we miss the ground state, and since that transition is exponentially small, we're going to. States that are crossed, these higher order excited states are crossed as the transverse field decreases. And that exponentially reduces all of these high order wave function dressings that made that exponent not 2 to the minus n when it's squared. And second is the perturbative mixing with low energy states. When I calculate these overlaps of dressings, these corrections to the wave classical states can change sign, which creates destructive interference in overlap. And this is not a calculation I can do anymore because it, all these zero crossings and not sign definite make this hopelessly hard. But both effects are expected to worsen scaling dramatically. And we can actually check this in sort of indirectly by looking at the probability of returning states that are any fractional Hamming distance from the true ground state. So Hamming distance is the number of bit flips. And so we looked at states that were within, and random state is n over 2 flips away. So fractional Hamming distances of 2/5, 1/3, 1/4, 1/5, 1/8, and 0 flips of the true ground state. And we fit all these to exponential decays. The 4 constraint densities we looked at are clockwise from top left. As you can see, the ground state, the probability of finding the true ground state is decaying pretty much the same, but the probability of finding states close to it, the decay becomes a lot softer in the more extremal problems. And these decimals here are all exponential fits for the inferred per state matrix element, assuming it scales as omega naught squared times density of states. And you can see that these exponents are rapidly approaching 1 as we get further and further away. So indeed, we are really seeing this destructive interference and weak field effects kill the ability to mix with higher excited states. And so, as I said, these are what we consider to be the limiting mechanisms for AQC and probably QAOA. But are they generic and inescapable? And in the last 10 or so minutes, or I guess 13 minutes of this talk, I'm going to argue that the answer is no. So we introduced in this paper a new method that we called spectrally filtered quantum optimization. And the approach here is, rather than optimizing the cost function directly, we're going to optimize arbitrary scalar functions of this. And again, we're going to assume, as I mentioned earlier, that the cost function is appropriately normalized. So random states have energy 0, ground state is minus n. There's a prefactor overhead of order nc for guessing this. And, which is, again, if we get a significant speed up, otherwise that doesn't matter. And what I want to highlight is that focusing on approximation hardness leads to a transition scaling that derives from global properties of the problem class, these hypergraph independent cost per flip curves, rather than any kind of fiddly specific details of instances. And that allows us to make really fairly confidently make powerful predictions. And of course, if you're someone who actually writes and works with quantum algorithms, you might ask, okay, well, how do I actually optimize an arbitrary scalar function of it? And on a NISQ machine, like any of the things we have today, the answer is you can't. The circuits are too difficult to do in practice. But on a fault-tolerant device that we'll have one day, then we can compute F by essentially mapping the value of HP to an auxiliary register of qubits, acting with F, advancing the phazon based on that, and uncomputing that whole sequence. And as long as our function is relatively simple and well behaved, like not singular, there's only a polylogarithmic overhead in system size. So on a fault-tolerant machine, it is really not any harder to optimize arbitrary scalar functions of f. It's just a polylogarithmic prefactor. And so, but to do things to actually get a performance improvement, we need to make good choices of these filters. And in the paper, we looked at basically two filter sets. One set targets excited states and attempts to preserve the per state tunneling rate over exponentially many targets, therefore preserving being able to find good approximations that way. Right. So basically, you keep the same number of states to find, but you make the rate stop collapsing so fast. Or soften the first order paramagnet to spin glass transition to a low order polynomial scaling through clever filter choices. And we're going to focus on the second option for this talk. So we're going to present a filter choice that ensures instance to instance stability for random hypergraphs in this approximation R regime of this paramagnet to spin glass transition, minimizes the influence of problem details on the transition structure, and critically overcomes the exponential scaling and pierces the entropic barrier. And all of this put together is embodied in an algorithm that we called multi-staged filtered optimization, or MSFO. We looked at two filter functions in this paper. Undoubtedly, there are two classes of function. Undoubtedly, there are many, many others that would work probably even better than this, but these work well. The first is a nonlinear folding transformation, which basically picks some target A, in this case we use A equals 1, and folds the spectrum in a nonlinear Maurer controlled by some power x. So if x is 1, it's a linear, like absolute value transformation. If x is equal to 2, it's a quadratic fold around energy A. Again, this is entirely done to the classical problem. The quantum terms are left, the transverse field's left alone. And then a spectral warping function that applies a sign-preserving fractional power. So basically a sign-preserving square root, for example. We begin with both filters composed. We're going to target the ground state. Again, we assume we've normalized this correctly, which is a guessing overhead. So pick A equals 1. And so we first apply the nonlinear fold filter, and then we're going to apply the warp filter over that. But we'll start with the folding filter first. And so in step 1, we are going to optimize this wacky filtered cost function just using the standard AQC approach. We initialize the uniform superposition, the ground state of the transverse field driver, and we leave that on all the time, and now ramp up the cost function to unit coefficient in some time t1. And we're going to predict the scaling of T1 very shortly. This is slightly different because we're not ramping the problem. We're not ramping the driver down yet. We're just ramping the problem up. And here I should say this graph plots the three filter choices. So the blue curve is the 1 minus 2x over n cubed of the random cost per flip, m flips away from the ground state. The gold curve is applying a quadratic fold targeted at 1. And the green curve is applying a fractional power of 0.6. And there's a reason for 0.6 that we'll get to in a minute over that. And so you can see that the random cost per flip curve that is so critical to determining the transition scaling is being pretty significantly changed by these filtering choices. Assuming that we can ignore transverse field chaos, we're bottlenecked by a single transition between the dressed ground states of our uniform, of our simple driver Hamiltonian, which now is dressed by the problem, or the filtered problem, and the dressed ground state of the filtered problem, which is corrected by the transverse field terms. And we choose a quadratic fold x equals 2 for the following reason. Once we've done this, the cost function classically is now actually asymptotically gapless. It's order root n flips to reach an order 1 energy cost, again with this normalization we're using throughout. And for random hypergraphs, you can show from simple statistical arguments that the local variation in the cost per flip is suppressed as order square root n over nc. So the more extremal it gets, the more suppressed those variations are. And the transition point is set by the energetics near the ground state. It's basically when, or as I'm varying the transverse field strength, or varying the problem strength rather, when do these two dress states energies cross? And by making the low energy structure of the classical cost function almost completely independent of problem details, we now have a transition point that's stable with high probability for these random approximation hard problems. The transition scaling is set by the overlap of the two states, which is exponentially many components. And this is therefore massively dominated by configurations with energies near the mean values. And we have more statistical arguments for why this is in the paper. So therefore, to predict the scaling of this transition, we can just use the average value for m flips away and invoke permutation symmetry to easily access the asymptotic scaling. Because once we've done this, you can easily you can calculate, assuming you can invoke this permutation symmetry accurately, you can find the scaling up to like thousands of spins on a laptop. This was on I did this calculation in less than an hour on the laptop I'm presenting this to you on. And absent warping, the transition remains first order and shows exponential scaling. And that's those blue dots there. So this is this mean field minimum gap. But I should say the exponent's a bit softer than no filtering at all, but it's still exponential scaling. But as soon as we apply the sign preserving square root fractional power, this warping transformation, essentially the exponent is getting softer and softer. And when w is less than 2/3, essentially lowering that power from 3 to 2, and that 1 minus 2x over n before us absolute filtering, etc. Once w is less than 2/3, it crosses over to polynomial. At exactly 2/3, it may be stretched exponential, I'm not sure, but for w less than 2/3, it's absolutely polynomial. Again, this is out to 1,000 spins, and you can easily go to larger sizes. And in particular, for w is 0.6, the transition scaling is essentially n to the minus 0.23, as opposed to exponential decay. And adiabaticity is ensured, and the transition into the dressed ground state succeeds if our runtime for this step scales as w over omega naught squared, or roughly n to the 1.46, right? So we're about n to the 3/2, again, compared to exponential decay. But we're not done though, because as I've said, all right, we've overcome the entropic barrier. This is probably enough for approximation hardness, but we need to do something more, because our classical cost function is still asymptotically gapless. And so if we just get there and then ramp down the transverse field, we're going to get significant heating and a lot of proliferation of local excitations. And our probability of actually finding the ground state is not going to be good unless we do a very long ramp to lower that down. And so in stage 2, we smoothly turn off these filter functions. We ramp x smoothly from 2 to 1, and w goes from 0.6 to 1, with the transverse field set to 1 this whole time. There's no phase transition when you do this. The gap doesn't close in this process. And so now essentially we're in the dressed ground state of the original problem. So now we can ramp kappa to 0 fairly quickly and measure the system. And the total asymptotic gate count is, the first step is the bottleneck, because that scales. And total asymptotic gate count we predict in the paper to be not worse than order nc squared n squared polylog n. To find the ground state, or at least states close to it, in these approximation hard problems. And again, so the punchline of this talk, most important figure and most important slide is this in this entire talk is this one, which is the numerical verification of this claim. And on this, we used a runtime of this first stage, or for each stage, just for simplicity, that scales as roughly n to the 3/2. And the theoretical prediction was, if we pick a runtime of n to the 3/2, we should get a constant probability of finding the ground state. And that should be independent of constraint density. We're invoking this sort of same universal mechanism of finding the solution in this quantum algorithm, only now it's not universally weak, but universally strong, at least for these random hypergraph problems. I don't claim this works for every possible instance. And when we did these simulations out to n equals 25, we saw essentially exactly that. As theory predicts, with some small n variation and a little bit of variation from one to the other, but all these curves lie on top of each other essentially at the end. And the top is the MSFO simulations for the 4 constraint densities. The bottom is TAQC rescaled to have the same runtime. And this is, for these instances at least, an exponential speedup as predicted by theory. And these numerical sanity checks confirm that if there's something wrong with this theory, it's for some subtle reason that would be interesting and only visible at some much larger end than we can access. We also looked at a different method in the paper called trial minimum annealing, shows a similar exponential speedup for finding approximate solutions. And the calculation that predicts its performance looks very different from this. And the fact that two different analytical calculations yield similar approximation guarantees through this filtered optimization method for random hypergraph problems really suggests to me that random hypergraph problems for max3 exercise in the approximation hard regime are actually quantum easy and classically hard. The derivations of both of these analytical calculations take advantage of statistical properties of this set and are not expected to apply to all instances. And so what properties ensure approximation hardness, like what detailed properties of hypergraphs would make them approximation hard in practice for quantum algorithms, are presently unknown. And I think we should figure out what they are. It's my view that essentially the space of problems that's approximation hard in practice is already some extremal corner of the space of all possible problems. But there's still a lot of stuff to find there. And within that extremal corner, the space that is quantum hard is some even weirder, tinier thing. But we assume it exists because if NP is not in BQP, it has to. And so figuring out what it is would be really neat. And so conclusions, again, the paper reference is up there on arXiv. Classical approximate optimization hardness is generic. It only applies to fairly rare instances, but the mechanism for it is pretty simple. It's entropic barriers. The mechanism for quantum exact optimization hardness is similarly generic. It's exponentially small gaps in transverse field chaos. And I should say these warping and folding transformations are expected to actually make transverse field chaos worse, not better. So they're not solving that problem, but transverse field chaos is not a barrier to approximate optimization. Quantum approximate optimization hardness is not generic. We don't know what it is. Spectrally filtered quantum optimization resolves the problems in AQC and QAOA and gives you a strong approximation guarantee for random hypergraphs, including these planet partial solution problems. This yields an exponential speedup, at least for random problems, not all of them, in the classically hard regime. We don't claim this holds for all possible hypergraphs. What ensures approximation hardness for quantum algorithms is unknown, and I hope in this 50 minutes I've convinced you that this is at least a very interesting question. And so just to conclude, I would like to thank all of you for listening to this talk. I would like to thank the funding agencies that supported this work, the Department of Energy through the SQMS Center, DARPA through the ARCHAMELS program, the National Science Foundation, and the Fujitsu Corporation for a very generous grant of classical supercompute time. And of course, I'd like to finally thank very much Zlatko and the whole entire IBM Quantum team for inviting me to present this to you all.
Eliot, thank you so much for the wonderful talk and very nice results. Guys, this is a great time to post your final questions here in the chat. So please do so. Maybe we'll just start with the broad question of, what can you summarize for us or tell us, what does this mean, or what does this tell us about experiments that one might want to think about on near-term kind of quantum devices?
Yeah, so that's a really good question. So near-term, near-term quantum computers are not going to be able to implement this filter function the same way you can't do a quantum Fourier transform at large size, because they're single error fragile circuits where, like in a standard QAOA circuit, a single error generally doesn't, it's a single error means you probably won't find the ground state, but it doesn't mean your solution is garbage. If your algorithm was otherwise going to find something very low energy, a single error might mean it's just slightly higher. For this filtered, a single error in the whole filtered optimization circuit will give you garbage. But what I think for near-term devices this does mean, though, is that the fact that we can get potentially significant quantum advantage for approximate optimization means that this is really what we should be looking at more with near-term devices. And I know there's been some very beautiful results from Q-Control and your team that came out, or Q-Control using one of your IBM processors pretty recently. I forget exact problem they used, but like more broadly, the whole quantum utility concept of layered error mitigation pushed these things a lot further than I thought they'd be able to be honest. I was less of a believer in error mitigation before those papers than I am now. And again, you can't error mitigate your way to doing filtered optimization, but I think I hope that this renews interest in approximate optimization as a good target for quantum computers. We also, the same collaboration has a paper on a different algorithm that's not quite as powerful, but still shows a polynomial speed up on these instances over the classical result and AQC, QAOA, that's coming out, and we'll post it to archive in a week or two. And that could be run on near-term devices. So sort of keep an eye out for that one.
Yeah, we look forward to that. So, sorry, just remind us of which that coming up piece is related to which part of the talk?
So it's a different algorithm that doesn't use the filtering transformation. So you could run it on a NISQ machine, and instead modifies the driver with some clever combination of AC fields and iterative updating. And we can show that this will converge to the ground state much more quickly.
I see.
But it's still in exponential time for the same instances I benchmarked here, just with a better exponent.
Mm-hmm. Good. Thank you, Eliot. There was a discussion or question earlier. If you remember your spectral filtered quantum optimization slide, you had a quantum circuit picture on that slide. It would be nice if you could give us a little intuition into why that quantum circuit has the structure it does. If that's possible, that would be great to hear more about that.
Yeah, absolutely. So basically, what this filtered optimization is doing is when I'm applying e to the I constant HP, right? That's the problem layer. The default way is to just, HP is a sum of all these product of three Pauli Z's. So I would just do these 3Z rotations over the problem graph, right? In the filtered optimization circuit, I add a register of auxiliary qubits and map basically map the sum using binary signed adder circuits of each constraint is now increments the register by ±1, depending on the coefficient of the bit string in the superposition. And then I've calculated the sum of all the constraints and mapped it to a register instead of advancing the phase directly. And then you, probably with some additional auxiliary qubits, you do your filtering transformation and compute f of e. Then you advance the phase by f of e, and then uncompute everything to disentangle the auxiliary qubits.
Thanks, Eliot. Yeah, maybe you want to take that question.
Yeah, sure. So the other algorithm that we call trial minimum annealing does exactly that. It does this warm start. And you do need a transverse field to get a collective tunneling event, but it recovers the same speed up for approximate optimization. So it will find states with a target energy of around, our floor is 0.6 without doing any of the warping. The warping could improve it, but about 0.6 approximation ratio. In practice, it's higher, probably 0.75 or better, using and in this similar low order polynomial time. So we do look at a warm start algorithm like that in the paper also. And that was the completely different analytical calculation I alluded to. And that one is actually a little trickier and more technical, so we don't present it in the talk.
All right, wonderful. Eliot, do you want to share anything else with us or final words before we come up here to closing?
No, again, if you're, okay, actually one thing. If anyone in the audience is an expert in the classical PCP theory construction side, please get in touch. That part of computer science is really challenging to understand. And I believe that intuition for what is going to potentially break down these methods and ensure approximation hardness lies in the structure of these gap amplification constructions. So if anyone in the audience is an expert on the classical approximation hardness side, please get in touch. I'd love to chat.
Well, Eliot, with that, I'd love to thank you very much and congratulate you again on the nice results. Folks, this talk will stay recorded. so you can go back and rewatch it. But the only time to have these live discussions is Friday at noon Eastern time. So don't forget to click like and subscribe. And with that, we will see you next Friday at noon Eastern. Take care.